Let us look at in the previous class we looked at the problem of uniform wall temperature, right. This is that isothermal wall kind of a situation. All the analysis, the integral, scaling, everything was done based on that, right. Let us look at for uniformity's sake what is a uniform wall heat flux. This problem is a little bit more complicated, okay, because you now have a wall, okay, which is no longer at a uniform temperature. You are supplying it with some heat flux which is Q double prime, which is equal to constant. That is what you have done, okay. And this brings about that your T naught now will be a function of your y, right. It has to be a function of your y now, right. That means that this is the y. So, it has to be a function of your y in this particular case, right. So, in other words, this T naught minus T infinity will be a function of your y, correct. But few things do not change, okay, and we will just show the approach. Few things which do not change, for example, Q double prime scaling as K delta T by this thing, this of course does not change, okay, because this is this is the very definition of the wall heat flux, right. That is what we have always used, okay, because at the wall you know it is a conduction problem basically. So, this is basically that, right, dt by dx, right. So, that is what we all already know, that this particular scale will be applicable regardless of whatever, okay. So, in this particular case, okay, let us see that for Prandtl number, once again do the methodology for Prandtl number much greater than 1 fluids. We always solve for the two extremes, right. Let us see that what will be the corresponding delta T and things like that. We know that delta T, okay, the basic scaling argument do not change, it is just that what we are substituting that will change a little bit. So, this G beta delta T H cube divided by alpha gamma to the raised to the power of minus 1/4, that was what our delta T was, right. If you recall, that was what it was, except we wrote it in terms of Rayleigh number in that case, right. Now, in this present problem your delta T is, we do not know, it is a variable quantity, right. But on the other hand you know that the delta T, the Q double prime is now actually known, right. So, why not use this expression right here, and from here delta T becomes Q double prime, okay, delta T divided by K, correct. So, that is what we are going to substitute it now into this particular expression, right. So, in this particular expression, moment you substitute it, it becomes equal to H RAH to the power of minus 1/5, right, where this RAH is different from the RAH that you have dealt with earlier, except that it is given in terms of the heat flux rather than in terms of the temperature. So, this is the definition of this RAH, okay. Now, several books will differentiate between this RAH and the other RAH, it is your choice. You can either write it as RAH star as Adrian Bejan has done, or you can write it in any other way that you want, but it is basically the Reynolds number, the equivalent definition of Rayleigh number, I am sorry. So, where it is given in terms of G beta H to the power of 4 Q double prime divided by alpha, the kinematic viscosity and the thermal conductivity, that is how this has been cast, okay. So, it is the Rayleigh number, we call it based on heat flux. That is the only major change that you have essentially. You have written it in exactly the same way because nothing should change, except that you have added one particular scaling, okay, which is basically Q double prime is equal to K delta T by the thermal boundary layer thickness, right. From there we are eliminating delta T, or the temperature differential, that is because that differential is not constant anymore, it is the Q double prime which is the constant over here, right. So, that is the only change that we have made over here, right. So, in other words, this delta T now therefore should become, let us not put Okay. So, you can see that both delta T as well as the temperature differential are proportional to h to the power of 1/5, right, okay, because h averaged quantities are proportional to h to the power of 1/5. Okay. So, the local values are proportional to the local values. So, these are will be the average values, the local values will be y to the power of 1/5, right. So, that is the standard. Okay. Because recall that a Rayleigh number actually has got a h to the power of 4. So, it is basically 1 over h to the power of 4 by 5 and you have a h here. So, that is how this h to the power of 1/5 comes into the picture, in case you are worried that how this h to the power of 1/5 came, right. Now, when we are dealing with local values, that at any y, okay, along the plate, this will become, instead of h, it will become y, okay, because that is the dynamic variable that we are actually dealing with. Okay. So, the Nusselt number here will be q double prime divided by T naught, which is a function of y now, minus T infinity y by k, right. So, for Prandtl number greater than to 1, the Nusselt number should scale as h over delta T, right. So, it scales as Rayleigh number to the power of 1/5 roughly, right, because your delta T scales like that. Okay. So, naturally it will be Rayleigh number to the power of 1/5. Okay. Got it. So, this part should be very self obvious. So, right. So, Nusselt number is like that, and if you recall the other two parameters, that means delta T is that, right. So, h by delta T is basically Rayleigh number to the power of 1/5, which is basically the scale for Nusselt number, and remember this definition of Rayleigh number. Okay. So, there is nothing great that we did, except that we have played with a little bit of variable, so that it applies to the current problem, right. Now, for low Prandtl number fluids, okay, once again the methodology is almost identical. Now, it is Rayleigh number, Prandtl number to the power of minus 1/5 is the same thing. Okay, there is absolutely no change. The delta T is q double prime by k h Rayleigh number h into Prandtl number to the power of minus 1/5, and Nusselt number is Rayleigh number into Prandtl number to the power of 1/5. Got it? So, these are the three results that you will get. Again, I am not going through the motion, you just substitute it, you will automatically get the Rayleigh number, because that delta T now comes in the right hand side also. So, that is why when you take it away to the other side, that is why instead of 1/4 you have now 1/5 dependence, and this Rayleigh number has been cast in a particular way. These are the only two things that you need to remember, okay, or you need to, you can do all the math also and you can come pretty much to the same conclusion, right. The validity of the scaling results can be checked by more rigorous analytical solutions. So, one such analytical solutions which is valid across by, this was reported by Sparrow, okay. This is like an adequate, this is like a curve fit, okay, and this is valid in the range of 0.01 Prandtl number and less than 100, about that, okay. In the two limits 0.616 into Rayleigh number to the power of 1/5, 0.644 Rayleigh number 1/5, Prandtl number 1/5. This is the general scaling, this is Prandtl number goes to infinity, this Prandtl number goes to 0. So, these are the two quantities that you would get, okay. But this is the most general scale that was found by Sparrow, right. These were the two most general scales that were founded by Sparrow, okay. So, as you can see over here, now we have shown that uniform heat flux is no different, okay, except that the scaling parameters have been adjusted a little bit to make sense, right. So, you can follow through the same motion, the same type of similarity arguments, the same type of integral analysis, and basically come to the same fact, right. So, that is what is most important over here, and we have finished this particular thing, and I can show you one other important stuff which is worth mentioning before we move on to the other things. Okay. If you take the case of the isothermal wall, right, isothermal wall, that is the first part of it, right. So, this is your delta T, which scales as y to the power of 1/4, we already told that earlier, right. This delta T is constant. So, naturally the fluid, okay, that is actually going up the wall, okay, going up the wall, okay, there the heat flux that it will carry will progressively go on decreasing, because the driving the temperature of the fluid is actually increasing as it is moving up, with the temperature of the wall being maintained at a constant, because it is an isothermal wall, right. So, naturally the quantum of heat that it receives, right, the heat flux shows that kind of a trajectory, right. So, it just is moving up like this. Okay. On the other hand, if you look at this particular situation, delta T is now scales as y to the power of 1/5, not 1/4, like in the case of an isothermal wall. Please look at it very carefully. Okay. What happens over here is that now the heat flux is a constant, right, heat flux is a constant. Now, to maintain that heat flux, your delta T has to show a profile like this, right, because you have to have a profile like this, because you have to maintain the same heat flux, right, at each point. This is very similar to the, if you remember your internal flow situation, where to maintain a constant heat flux, okay, you had to do this. Okay. So, the temperature profile here shows as y to the power of 1/5 dependence. The thermal boundary layer showed a dependence of y to the power of 1/5. Here of course, it was 1/4, and here it was the q double prime depended as minus 1/4. That means it shows that exponential nature of this decay, right, because it is a power law. So, it is y to the power of minus 1/4 is like a power law, right. Here of course, the temperature increases, but at a scale which is y to the power of 1/5. That means the slope is not that sharp. That is why you have a more flattish type of a profile. That is what we proved just now, that delta T is basically dependent as y to the power of 1/5, right. So, y to the power of 1/5 means, okay, that the dependence, okay, is going to show a gradient which is very shallow. So, this is exactly how this has been drawn. This gradient is very shallow, right, whereas this gradient is large, because this is minus 1/4 variance, right, of q double prime. Got it? Okay. And naturally, the delta T also varies in this y to the power of 1/5 kind of a variation. So, this is even flatter, right. This was 1/4, this is 1/5. Okay. So, that should have a slightly sharper kind of a increase compared to this, correct. So, that is how these two figures have been drawn. You can see that there is a little change. This is a little, this slope is not that high, but it is a little bit more than this, okay, because of the 1/5 and 1/4 variance. So, it is more like these boundary layer profiles are almost like constant thickness as they move along the plate, okay, when you particularly so when you deal with the situation of a uniform heat flux, right. But however, uniform heat flux decays quite rapidly because of the minus 1/4 dependence. Okay. The delta T however does not increase that much, it just increases a little bit because of the y to the power of 1/5 dependence. These two dependences are the same. So, these two profiles should also look like the same. So, you can just sweep it, and you can with appropriate scales, okay, if you place on the one on the top of the other, they will be exactly the same profiles, right. So, that is exactly what we are seeing in this particular case. Okay. So, this gives you a good idea that how the constant the isothermal wall and the uniform heat flux profile should look like, how the temperature should vary, how the heat fluxes should vary. Okay. So, this is an important visual concept, okay, because you have got all these expressions. Now, you need some kind of a visual feeling that how this profile should look like. So, if you do the math, you can easily identify these things yourselves, but even if you do not do the math, these are the kind of profiles that you will get, which all comes from scaling, all comes from the mathematics that we did so far. Okay. So, based on this, okay, we next go to a slightly more realistic situation, okay, which is called the thermal stratification. We will pose this problem, okay, and we will pick it up later, okay, as with time, right. So, thermal stratification is an interesting thing to begin with, right. So, we are talking about, you know, this isothermal walls placed in an infinite reservoir of fluids. There is I mean, it is not a shallow thing at all, right. It is like a small wall which is placed in a large body of the fluid, right. But this is obviously the simplest model possible, but it is not exactly the case when you actually deal with realistic situations, right. Realistic situations, there will be a ceiling of some sort, right. There will be a ceiling at the end of the day, right. So, that ceiling will pose a restriction. So, that means there is a finite height. If I have to put it like that, it is a finite height, okay. So, it is a finite height, and the boundary layer and the heated boundary layer eventually hits the ceiling. It has to hit the ceiling, the boundary layer, okay. So, what happens when it hits the ceiling is that if you have this kind of a situation, right, what will happen is that it will go up, it will hit the ceiling, right. What we will do, it will start to discharge in a horizontal direction, this heated fluid, right, because if it meets the ceiling on the top, right, there is no other way that it can go, right. So, it will go and hit the ceiling, and then it cannot penetrate through the ceiling, right. So, it has to go in the horizontal direction, or rather it is forced to go into the horizontal direction in this particular case, okay, and then it can climb down and complete the circuit, right. So, that is what we would normally have. Now, this has got a long term effect. This happens in any room that you will see, okay. What will happen is that because of this, you know, finite size of the whole thing, after certain period of time, there is of course a developing time scale during which all this dynamics happens. What you will find is that the room will become stratified in the sense the bottom of the room, okay, will have a slightly lower temperature from an ambient perspective, and the top of the room will have a slightly higher temperature, right. So, that means here if I have to do it this way, so if this is the height of the wall or the height of the ceiling, whatever you call it, right, okay. So, that is the thing. So, here the temperature is T infinity 0, right. So, that means it is the ambient temperature at the base of the room, so to say, right. It goes up, assuming that it is linearly stratified, it goes up to another temperature which is basically given as T infinity H, right, okay, some T infinity H, and the temperature at any particular section, right, at any particular y is given as T infinity 0 plus gamma y. This gamma is not the kinematic viscosity, this gamma is some slope, right, okay. So, that is what the thing is. So, that means here at this point the ambient temperature is a lot higher than whatever is the temperature at the base. That is because the room has gone stably stratified. The lowest is the coolest, the top is the warmest. This happens in many of the rooms, okay. If you will find that in many of these rooms, okay, which operates on natural circulation, you will find this kind of stratification is obvious. That is because the heated air, okay, encounters the ceiling, okay, and it kind of stays there, okay. So, it over time it basically increases the temperature of the room in that particular linear way, okay. So, that is the most important part of this particular argument. So, of course, when this slope is 0, you get back your originally non-stratified situation, okay. However, when this slope is not 0, you basically have different levels of linear stratification. So, if this slope is very high, that means you have a lot of stratification, and when the slope is a little low, okay, you have a very little amount of stratification. One other thing that should be clearly mentioned over here is that as you increase the level of stratification like this, right, that means you have temperature going up to infinity h, T infinity h, what will happen to the heat transfer? It must actually go down, right. That means it becomes a more ineffective way, that is because the driving potential is still your T naught minus T infinity, right. So, your T infinity is going up. So, naturally this will affect your delta T. So, effectively you are reducing the delta T by increasing the temperature of the ambient. So, naturally there is that correspondence, right, that driving influence which drives the buoyancy, which drives this entire recirculation loop, that is going to become a little weaker, okay, for the same given wall temperature. Remember, the wall temperature is still the same, right. So, that is a very important argument over here, okay, and we can write this particular parameter as B, which is like a stratification parameter, gamma h divided by T naught minus T infinity naught, right. So, B is equal to 0, okay, when this thing is fully this thing is not stratified at all, and B is equal to 1 when it is fully stratified, right. Got it. So, that is the most important part. Okay. Now, we will see now how to analyze this particular problem with the understanding that the overall heat transfer rate okay, will come down with gamma. As gamma increases, HTR comes down. That has to be the case, right. Okay. So, let us look at now this particular problem and see what can be done. So, in this particular problem, let us assume delta T is equal to delta, so avoid any velocity and thermal boundary layer issues. So, T minus T infinity is equal to T naught minus T infinity into 1 minus x by delta T square, right. V is equal to capital V into x by delta 1 minus x by delta square, okay, and you have that additional thing T naught minus T infinity is equal to T naught minus T infinity plus gamma y, right. So, now if we do the integral approach, the momentum equation, okay, the momentum equation 0 to x v square dx minus gamma dv by dx at x equal to 0 plus g beta. Check all these calculations when you actually do the entire exercise at home. Sometimes it is better if you do some of these things at home also. So, the energy equation becomes d by dy 0 to x v T infinity minus T dx is equal to alpha dt by dx x equal to 0. Okay. Now, what we do? The basic part after this is basically to substitute. T is there, V is there, substitute it in the energy equation and in the momentum equation. Both needs to be substituted in both the cases, right. So, the momentum equation, let me just write it quickly, d by dy okay, and this can be even shortened a little bit. Okay. So, now that we have this problem, let us just define, before we end this class, define the non-dimensional parameters, okay, and then cast it, and then we will pick it up in the next class and do a more detailed discussion on the results. So, we can define y bar is equal to y by h, and delta bar is equal to delta by h into Rayleigh number to the power of minus 1/4, right. V bar can be taken as V divided by alpha by h. These are the natural scales of the problem. So, there should not be any issues in you understanding that why this is coming out to be like that. The Rayleigh number h, however, has been defined based on the initial, that means on the lowest temperature, that is the T infinity. This is the temperature at the bottom of the plate, and B is of course equal to gamma by h divided by T naught minus T infinity comma 0. Okay. So, these are the 5 non-dimensional parameters that we have defined. B is the new one. These are common parameters, and the why we have normalized it by these scales should be pretty apparent, because these were the scales that we used in our measurements anyways, right. So, based on all these things, in the next class what we are going to do, we are going to put these parameters in the momentum and in the energy equation, and we are going to solve it, and we are going to show that what the Nusselt number and the heat transfer rate is going to look like. Okay. So, see you in the next class.